The idea of the paper is quite simple. There is this concept called multi-packet reception. Multi-packet reception is the capability that the receiver can decode multiple packets transmitted at the same slot. How is this achieved? We're dividing, let's say, a resource grid in frequency and in time. To use it in a better way in the OFDM systems, we're dividing it into frequency and time, and then each user is sending packets in their specific time and frequency limits. Receiver is able to decode all different packets separately. But the idea is, let's get rid of this limitation to divide wireless resources in frequency and time, and then without any boundaries, we send packets overlapping to each other in frequency and in time. And they have certain characteristics, and these characteristics can be in terms of code, power, or something else. But then the base station can still decode the 4 packets. This is a physical layer improvement. It's discussed under the name of NOMA, but it doesn't have to be NOMA. There are also other techniques. But this is something that I will not discuss. What I will say is this is a technique that we think it's available, and then let's abstract this in medium access control as multi-packet reception capability. We call this KMPR. And we assume that the physical layer provides this capability. Legacy we call 1MPR, which is one multi-packet reception, so multi doesn't make sense there, but it's fine. And then the new ones is KMPR. Then if the receiver is too good, or if the noise level of the communication is too good, then you can reach higher KMPRs. If it's not, then you go back to 1MPR. So that's the idea on the physical layer. And now the question is how this multi-packet reception affect the access algorithms. In that sense, random access algorithms. Chetomir has already worked with multi-packet reception using slotted Aloha. Basically, what he showed with slotted Aloha is, I don't have a quick access to his paper, so I couldn't open it. So you have to believe me for saying this. But he shows that increasing MPR increases the throughput of slotted Aloha in general. And we want to investigate how does it affect the tree algorithms. His initial insight was, actually he also did a bit of analysis himself, and then he realized for some cases in tree algorithms, it doesn't improve the throughput at all. And then he said, okay, let's check this. If that's the case, then we can conclude that to use tree algorithm with multi-packet reception doesn't make sense. And this is what we wanted to investigate in this work. Okay, and then there is a lot of yada yada yidi. Maybe it makes sense to go over this example here. On the picture A and picture B, you have both 5 packets that have collided. On the left side, 5 packets collide, and then we have a 1MPR scenario, and they split. So 3 users, or 3 packets, pick the upper slot, and it's still a collision because we are on a 1MPR scenario. And again, they split, then 2 users select the same slot, then it's again a collision, and then finally the users split 1-to-1, it's a success, then we go back, then 2 users were up here, so then it leaves 1 user, so that the remaining user chooses this one, so it's 1 user again. And then we go down, blah, 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 the same splitting is done. And then all in all, we need 5 slots here, 5 slots there, 1 slot here, 11 slots to solve a collision of 5 packets. And then we have a throughput around, I guess, 40%. In the KMPR case, where K is, I think, 2 here, when 5 users split 3-to-2, so normally in the previous case, 2 was a collision because we had a 1MPR scenario, but we since we are 2 ampere here, this can be decoded, so it's not a collision anymore. On the upper part, the 3 is still a collision, and they have to split again, and then they split 2. Since we are at 2 ampere, it's not a collision, so it's a success, and then 1 is also a success, and then in total we have 3, 4, 5 slots to solve a collision of 5 packets. And then can we say we have a throughput of 1? Not really, because as I have drawn you with my amazing drawing capabilities, the kmpr slots requires more resources. So to make it a fair comparison, we have to multiply each slot with 2. The slot size is smaller on here and bigger in here, and then basically you have 10 slots used for a collision of 5 when we multiply it with 2. So then it's already from this example, you can see that it doesn't bring too much gain, but we will investigate that later, and we will end up with different conclusions, luckily. So kmpr brings some gain for a certain setting of 3 algorithms. So that's the general approach. Are there any questions until here?
Actually, I couldn't get why do you multiply with 2 in
The same.
kmpr?
The same thing for me, actually.
So Shannon capacity is fixed, and W times logarithm of 1 plus SNR. And then this is a rate, so we can also, to convert this to a payload, we can multiply this with time also, right? But we cannot go over the Shannon capacity. Do you agree to that?
Yes.
The twice payload in the same space that is defined by the Shannon capacity is not possible. And if you're fitting twice the payload, which is T times C here, then either we are increasing W, or we are increasing T, or we are increasing power, or something like this. And then, as you see, if we increase power, we are increasing logarithmically the amount of resource we use. If we increase W or T, we're increasing linearly. And basically, if we enable kmpr, we assume that we increase it linearly. This means we are increasing W or T linearly. And subsequently, we can say that the twice amount of bandwidth is needed for 2 ampere compared to what you would need in 1 ampere.
Yeah, but this is taking the assumption that OMA already achieves the capacity of Shannon. Because the idea is that NOMA can actually achieve it, and that's why, because in NOMA, I think this W can be used by 3 users at the same time. Like they can transmit at the same time on the same frequency.
Of course, the intuitive idea is that, yes, please.
Wouldn't SNR be dependent on which layer you are of NOMA?
Layer? What do you mean layer?
So you have the first user, where the second user is attributed as interference.
Okay.
And then for the second user, you have the third user as interference, and the residuals of demodulating the first user and the background noise.
True. So basically what you're saying is let's say the capacity in a multi-user scenario looks something like this. So this is user 1, this is user 2. And basically, let's say this is the rate region. So either you can, and this is C, okay? Either you can go with full capacity 1 user or full capacity other user, or you can go somewhere in between. Discussion with NOMA is when you're trying to do non-orthogonal multiple access, they say this is the rate region that you're walking on. And if you are enabling NOMA, you move on to the red region, because you get rid of the imperfections caused by the OFDMA, where probably you need guard bands or I don't know what, or like intra-band emissions or something like this. And then this is what OMA enables, they say. But as you see from this figure, which illustrates a two-user scenario, the Shannon capacity is never exceeded.
Mm-hmm.
So what NOMA enables is not overcoming Shannon capacity, it's actually reaching Shannon capacity. So basically Shannon capacity is our postulate, or like is our limit in wireless communication. What Jörg was mentioning, yes, please.
I'm sorry, I didn't want to interrupt you, because I was doing some research on this also with the interference cancellation. Basically, it's all the same. You have one huge problem with NOMA that I'm not sure if NOMA really improves the total capacity, because you have to reduce the coding.
I fully agree. So in
the
the end,
modulation.
It's a theoretical concept, and when you put it on the hardware, you cannot really reach where this red arrow brings you, but maybe you're somewhere here or maybe somewhere here, depending on your hardware. So in the end, it's not always guaranteed that NOMA will enable this, or some other technique that I don't know. But we assume that this KMPR is somehow enabled. Okay, so there are multiple points. So is it clear why we scale the initial resources needed for KMPR resources linearly compared to 1 MPR resources? It's clear first.
You mean the initial resources?
Exactly. So what 1 MPR, maybe we can give an example. Maybe 1 MPR needs W 1 log 1 plus SNR to send the packet that it's sending, and then similarly the 2 MPR will need then 2 W1 log 1 plus SNR, assuming that the user's payload is the same, and then with 3 MPR we are decoding 2 packets. So we need twice the capacity basically to be able to decode 2 packets.
And now I think I get it.
Okay.
So the idea is that the only improvement is just faster.
Yeah, it's also flexible. That's the idea. On the scheduled access, you need to tell which user to use which resource, and in here, any random 2 users, you can decode.
Mm-hmm.
That's the advantage.
Okay, I see.
The implementation of KMPR we also assume exists. As an example, we cite the NOMA work. But maybe there are also other works that enable such KMPR. Okay, so that was the 2 points that I wanted to clarify before going on. Did you understand in general how the 3 algorithms work? Users giving random decisions that will lead to different decisions, and these different decisions eventually leads to decoding of users' packets. And this is done in a, let's say, decision tree manner. So whatever decision you have done at the beginning, you stick with it, and then you give another decision which leads the separation of the user. So you don't just give up your decision and then reset. You just say, okay, this is I decided and I stick with it, and now I give another random decision.